Hi everyone, welcome to this episode of Keipert Labs. In today's video we're going to be looking at predicting entropy changes in a system. We're just going to start by recapping what we understand about entropy and looking at a change in entropy, which is delta S. We're going to look at how we can predict entropy change based on what's happening in the system. We're looking at standard entropies, seeing how entropy connects with Hess's law, and looking at the second law of thermodynamics. So firstly, we've introduced the concept of entropy, thinking about the way in which energy can be spread out amongst a system of molecules. We've seen that it connects back to the concept of a microstate, which are the possible configurations of energy and molecules in a given system. The more possible microstates, the higher the entropy is. And this helps to bring back to chemical reactions because we can recognize that all processes are driven are stimulated or caused by the spreading out or dispersal of energy amongst particles. So that is a change in entropy, particularly thinking about increasing entropy. And there are a number of ways that this can happen, that the entropy of a system can be increasing or delta S can increase. So this change, so an increase is a positive delta S, a decrease in entropy is a negative delta S. Okay, so if entropy is decreasing, we're becoming more ordered, we're going into a system with fewer microstates, more stable, things like that. Okay, firstly, what we can, increasing the number of particles will increase the entropy because the energy that we have in the system can be spread out over more particles. There's more possible microstates by having more particles, which means that entropy increases. This is especially relevant in gaseous systems because the particles are much freer to move. And so the particles can be more physically spread out as well as just they're spread out of energy. Temperature changes will also affect entropy because the more energy that's supplied, so the more energy that these particles have because of their motion, their kinetic energy, there's more energy that we have to spread out over the particles, so therefore entropy increases. So for example, if we're looking at heating, we're looking at Q equals mc delta T, that as the particles have a greater amount of energy at that higher temperature, that then there's more energy to spread. Okay, so that's kind of how we can look at it. Phase changes also affect entropy because the more energy that we supply to the system to change from solid to liquid or gas causes a greater freedom of particle movement. That means that there is, that those particles are moving around more. There's lots of possible more microstates, more configurations they can have, so entropy increases. So as we go from solid to liquid, liquid to gas, entropy increases significantly. Okay, we can see that if we look at graphing entropy versus the temperature, and seeing that as we have a solid and its temperature is increasing, that the entropy continues to increase, and then we get to a certain temperature at which that is undergoing a phase change. We're going melting, and then over here we've got boiling, where entropy is increasing vertically when the temperature isn't. Okay, because we're changing from a more ordered to a less ordered state with more microstates, more possible configurations. Okay, the change related to fusion, that is the change at the melting, and the change at the boiling or vaporization represented those little vertical sections. Okay, so from solid to liquid to gas, entropy increases. If we change the volume that is available to particles, particularly in gas systems, then that's going to affect the entropy of the system as well. You can see in these two images. First, we have a box with the red gas particles, but then a divider in the middle. If we take that divider away, and so now the particles can move into the whole box and spread out that way, or if we take one where we've got particles of two different gases, or even you could consider these to be liquids as well. We take a divider away and they can mix. So even though there's still the same number of particles, because each of those pink and blue particles has twice the space in order to move, in which it can move, affects the entropy of the system. When we have more available volume, the energy is more physically spread out. Okay, that the more spread out those particles can be, the more possible microstates that we have, so entropy increases. So for example, diffusion of gases or dissolution of a solid into a solution, or mixing liquids together, this sort of thing is applying. So now we can have a look at, say, right, well, these are things that are going to increase entropy. They're going to have a positive delta S. Now we can connect that back to certain types of chemical reactions or processes as well. We can look at a process and look at, okay, what sort of thing is happening here, and therefore what kind of entropy change are we going to have? So, for example, a decomposition reaction where we go from one particle to many particles, 2, 3, 4, is going to have a positive delta S. So like the decomposition of ammonium dichromate, this substance here, we're going from one particle to 3 different types of particles. We're forming 6 particles altogether, 1 plus 4 plus 1. So that increases our entropy. We just talked about phase changes from solid to liquid or liquid to gas. Okay, that's going to affect our entropy. So reactions that consume solids and produce gases or liquids will increase the entropy because we have more particles that are produced, perhaps, but also that those particles can spread out. So if we use up a solid but produce a gas, we've taken particles which are contained or constrained into a certain space, produced a substance that can spread out through the system, so we've got lots more ways that those particles can be arranged, so it's greater entropy. However, we do have some situations where we have a negative delta S. That is, we create a system that is more ordered, that has less randomness, that has fewer microstates. So synthesis reactions, where we take smaller particles and we connect them together, so like 3 oxygen molecules becoming 2 ozone molecules, that has a negative delta S. Or the production of ammonia in the Haber process, we go from 4 particles to 2 particles. Okay, so we reduce the entropy there. The reverse phase changes of what we looked at before, that is freezing or solidification, condensation, will decrease the entropy of the system. Okay, so we can see that by looking at what's happening with the particles, we can predict what's going to happen. But how do we actually measure something? Well, we need to be able to look at the scale of how entropy is measured. We need to look at standardizing it. So what we say is that at 0 Kelvin for any given substance, that it has 0 entropy by definition. Okay, because there is no energy in the particles at that level. All the possible energy in that system has gone, so we say that's 0 entropy. But as soon as we go to a value higher than that, we say, all right, well, the entropy that it has there is the difference from when it was in its standard state at absolute 0 up to the amount that it has at that point. Okay, so the standard molar entropy. Okay, so it's S, and then it's given that little standard kind of symbol that we've looked at previously. Okay, so the idea is that rather than being a relative scale, that because we set that at 0, that we're talking about an absolute scale. Okay, from 0 entropy at absolute 0 all the way up to the point that we are measuring. Now, one of the things that makes our job easier when we're making calculations about entropy is that entropy is a state function, like enthalpy. That is, the change in entropy only depends on what the initial and final states of the system are, not on how we go from point A to point C or point F. Okay, so if we go directly from A to C, or we go via step B, that the overall change in entropy will be the same, which means that we can use the fundamentals of Hess's law to calculate the changes in entropy the exact same way that we've looked at changes in enthalpy. Okay, so looking at the difference in the sum of the products minus the sum of the reactants, looking at those sorts of values, they all give us useful information there. So we can use Hess's law to calculate entropies of reaction the same way as enthalpies of reaction, which is particularly useful for, like before, for reactions that we can do directly, that we can actually kind of work out and say, well, what would be the change in entropy for this hypothetical reaction based on looking at the pieces and adding them together. Now, the second law of thermodynamics, thinking about the way that the universe functions as a whole, is kind of this big umbrella concept that helps us to understand why a change in entropy why does an increase in entropy tend to make processes spontaneous. Okay, so what we are saying is that, so the second law of dynamics, all processes in an isolated system, that is one that doesn't exchange either matter or energy with the surroundings, all these processes go in the direction that increases the entropy of the universe. Okay, so that is, overall in the universe, entropy is increasing. The processes that are going to favour that are the ones that will be favoured. Okay, now one of the things to keep in mind is that the entropy of the universe is the entropy of the system, that little part that we happen to be defining, the particles that are involved, the box that we're focusing on, or whatever, and then plus its surroundings, which is the rest of the universe. Okay, so if we're only focusing on a certain number of particles in one container, then the universe, the surroundings, is obviously everything else, which is very significant. But the idea is that we need to consider the entropy aspect of the system and the surroundings as a whole to be able to decide if a process is going to be spontaneous. And I'll show you why. Okay, so the idea, so looking at the way that the entropy works, if we have a change in the system entropy that's large and positive, that is, it's a big increase in entropy, then the entropy of the universe is going to get bigger. Even if the surroundings decrease a bit in their entropy, if the system gets a lot bigger, then overall we're talking an increase in entropy in the universe. Thinking about the connections to do with enthalpy, thinking about exothermic reactions. Okay, so if we have a large and negative enthalpy change, that is, so very exothermic reaction, we're going to get a large energy transfer from the system out to the surroundings. Therefore, this energy is going to be well and truly spread out through the surroundings, going to make the entropy of the surroundings higher. So the reason that we bring this up, talk about this now, is that in certain processes, like the burning of magnesium, that the system entropy goes down. We are taking a few, more particles and we're combining them together to make fewer particles, so the entropy of the system goes down. So you might think, okay, well, if we're trying to increase entropy overall, surely that wouldn't be spontaneous, it wouldn't happen. But yet, you've probably done it in the lab many times in your life, that it does happen. So the fact that the surroundings entropy increases helps to explain why, on balance, this process is even able to happen. Okay, so because the entropy of the surroundings increases by a lot more than the system goes down, that this overall principle is being obeyed. Okay, so I realize this has been a pretty heavy going kind of video. These aren't simple concepts, and we're going to unpack them further in a range of different ways from here. But so we talked about what we mean by a change in entropy of the system, seeing how the change in entropy and how we predict it to be based on what the system is doing gives us information to work out whether certain things are spontaneous. We looked at how we can measure standard entropies relative to the entropy of zero Kelvin, and seeing that the increase up to wherever we're measuring is a standardized value. We're seeing that because entropy is a state function like enthalpy, that doesn't depend on the pathway that it goes, that we can use Hess's law to be able to determine entropy changes for anything that we come across, as long as we have the data for the pieces. And seeing how the second law of thermodynamics, this big picture idea to do with entropy, helps us to explain and account for why some processes are spontaneous and others aren't. Thanks very much for watching. Bye for now.